normally use Bayesian theorem to condition the later on the former, okay, to condition the unknown on the known, okay, in other words, to condition, I think, last chapter we already talked about this a lot, so I will not, if you write the formula, we know that, very well. I just erased it. Kind of feel like I shouldn't erase it, actually. Anyway, okay, so generally we refer to the knowns as data, okay, treated like a constant, okay, the unknown as parameters of your model, actually, okay, and treat them as probability distributions, okay. So the Bayesian inference or Bayesian data analysis is to eventually obtain the distribution, okay, posterior distribution of these parameters, okay, conditioned on the known, okay, which is conditioned on the data, okay. So in more formal terms, we assign probability distribution to unknowns quantities. Then we use Bayesian theorem to transform the prior probability of probability distribution into posterior distribution. We have talked about this. Several lectures already. Okay, so here users specify a full probabilistic model by writing a few lines of code. Okay, and then inference follows automatically. Okay, this automatically is an important thing. Okay, of course. Okay, you can control this inference. Many options of this inference. By yourself, but you will be surprised to find that. Okay, the modern Bayesian inference package, such as PyMC3, or for example, like some package under the R, okay, they are able to do this inference automatically, and the result is already good enough, okay. So I will show you, through example later anyway. So this will enable practitioners, okay, the people like us, to build complex probabilistic models in less time-consuming, less error-prone way, because, well, you don't need to play with the parameters, you don't need to play with those options. Basically, the package already can already decide them for you automatically. Okay, so the probabilistic programming language, this impact on data science is like a fortune programming on scientific computing. I don't know, maybe nowadays nobody knows fortunes anymore, right? Anyone knows fortune in this room? You nod your head. You know fortune? Yeah, we know the term, but has anyone in this room have ever written a fortune program? I don't think so. But back to like, to be honest, even when I was a student, fortune is already outdated. Okay, when I was a student in computer science, because when I was a student in mathematics, my undergraduate degree is in mathematics from 1987 to 1991. At that time, I think fortune was still popular. But after I went to US to study computer science, that was 1993. Nobody used fortune anymore, okay? At that time, people are talking about C, okay? And I think like Java was newly invented at that time, okay? And people talk about OOP a lot, okay? So think about this, okay? So Fortran was actually very, very popular, like back to like 1980s, okay, 1980s and early 1990s, okay. Without Fortran, to be honest, like we don't have like the you know, we know like the U.S. sent the astronauts to moon, right? So I mean, in that mission, okay, all the codes were written in Fortran. Okay, so it was because nowadays nobody knows like you know, after a couple of years, like 1990s, nobody knows like Fortran anymore, right? So it becomes so difficult for like the NASA to maintain those like you know old system, you know. So they have to rewrite everything, you know. But you can see like how important Fortran was like in old days. But you know, so Fortran has a big impact on like scientific computing. But unfortunately, you guys didn't know. But I just want to emphasize probabilistic programming. Okay, not necessarily PyMC3. Okay, because as I said, there are like other probabilistic programming libraries out there. Okay, in R. Okay. And to be honest, like because like in this field, actually like more people use R, and it's like or like Winbox. Okay, there's like also some package under like Windows. Okay, more people use those like package than the PyMC3. To be honest, okay, but this is the only one I can find. Okay, that is supported by Python anyway. Okay, so anyway, a probabilistic programming language, this is PPL, hides the detail on how probability are manipulated, how the inference is performed from user, allowing users to focus on model specification and the analysis of results. So how this analysis, how this inference is done, okay, I will not discuss that aspect in this chapter. I'm going to just talk about how you can do this inference through programming, okay? And the inside mechanism, how this is done, okay? Remember I told you like the NCMC, right? The Monte Carlo, like Markov chain Monte Carlo, okay? The sampling technique. I told you that is very important in Bayesian inference. Okay, but I will not talk about that. This chapter, okay, in this chapter I will only talk about programming. Okay, that part will be discussed like later. Okay, I will talk about that, but not right now. I want you to understand how to do the probabilistic programming first, and then I mean you are able to play with that, which will be, well, part of the questions that I asked in the homework too, by the way. Okay. So for PyMC3, okay, what is it? Okay, it's a Python library for probabilistic programming. Okay, and its base code is written using Python, and the computationally demanding parts are written using NumPy and Thano. Okay, NumPy, you guys know, is part of like a Python, like a computational library. And Thano is actually a library for deep learning, okay? And to be honest, Thano is now discontinued, okay? The support for deep learning. It's because like in deep learning, everybody use like PyTorch or like TensorFlow or like Keras. Nobody use Thanos anymore. Okay, maybe because like we don't like the end game, right? I mean, just kidding. But Thanos, this Python library is no longer that popular. Okay, but PyMC3 is based on Thanos. Okay, So no, this Theno allowed us to define, optimize, and evaluate mathematical expressions involving multi-dimensional arrays. Okay, because in deep learning we deal with those things all the time. Okay, so that is why, like Theno is very good at this type of tasks. Okay, which happen to be also very important in probabilistic programming. Okay, so well, the reasons for PyMC3 use Theno. Okay, some of the sampling methods, such as no U-turn sampler. Okay, abbreviated as NUTS. Okay, this is like one of the advanced sampling techniques. Okay, and is well, any sampling technique or advanced sampling technique are one of the MCMC methods. Okay, but just for now, just remember this NUTS is one of the sampler. Okay, you don't need to worry about how this is done. Okay, we will talk about this later. Okay, I mean the concept and everything in more detail. Okay, so this computation, okay, need gradients to be computed. Okay, if you are into deep learning a little bit, you will know like computing gradient is actually essential part of like deep learning. Okay, in model training. Okay, so Theno know how to compute gradients using the automatic differentiation. Okay, so yeah, I will not go into the detail like about automatic differentiation. Well, because I'm also teaching deep learning, so if you are interested in knowing more detail about, I mean, how this deep learning package compute the gradients, yeah, feel free to take my class next semester. Okay, so Theno compile Python code to C code, so that is also makes the PyMC3 like efficient. Okay, it can be run very fast. Okay, so as a first example, let's see how we can write a program for the PyMC3 program for like a coin flipping. Okay, so for coin flip, we have tried to consider it using like a grid approach, right? We have tried to consider this problem using the conjugate prior, right? So this is the third time we consider the exact same problem. Okay, so now first we set a random seed, trials equal to 4, so theta real is 0.35. This is like the real theta value, which is unknown. Okay, which is supposed to be unknown. Okay, but we define it here so that we can generate the data based on this real theta value and see like if like analysis result match this real theta well enough or not. Okay, so data equal to stats Bernoulli. Okay, RVS. Okay, so so we use this theta value 0.35 and the trial to generate like the data. Okay, which consists of several flipping result. Okay, it could be 0, 1, okay, 4 of them. Okay, by the way. So for the likelihood, we'll use the Bernoulli distribution. Okay, with n equal to 1, the p equal to theta. For the prior beta distribution with the parameters 1, 1. So 1, 1, if you remember, I mean, this is like a beta distribution. So if you remember that when you assign A and B both to be 1, okay, it is flat, right? It's a uniform distribution, okay? So it looks like this. Remember, we talked about this like not only this one, but also we use a figure. You remember, I told you that's Krusk, like a diagram. Okay, in the last chapter, actually, okay? So how do we write a program for this model? It's simpler than you think, okay? So with pm.model as our first model, so here, okay, we create this first model, okay, and we specify theta, okay, which is drawn from the distribution beta, and that theta just is a name of this distribution, and alpha equal to 1, beta equal to 1. Okay, that's very, so theta is drawn from this probability distribution. And then when you have the theta, okay, and you assign the p equal to theta, and well, that's the y is the data, okay. Observed equal to data. Remember, we generate those 4 trials. We feed that into this Bernoulli, okay. Bernoulli is our likelihood, right? Okay, and this is our y. And then, okay, here, we sample, we do this, we call the pm.sample, okay, for 1,000 times, okay, with a given random seed. Okay, you can change the random seed, okay, if you want different sample, by the way, okay, and we will store all the result in the trace, okay, this is an object, okay. Yeah, I mean, the following basically, I mean, yeah, I think I will not go into every single line. I mean, basically, I already told you like this program, okay? So if you want, I mean the explanation, like, you know, in more detail, you can check out like the slide, okay? So the last line, okay, is the inference button. So you can see that, okay, this pm.sample, we didn't specify a lot of information, but you know, this sampling process, okay, this sampling process is going to generate the posterior distribution for you, okay, automatically, without the need for you to set up like a lot of options. No. I mean, it will just generate this, you know, this inference button. So once you have that, okay, so it means we are asking for 1,000 samples from the posterior, and we will store them in the trace object, okay. So if you run the code, it looks something like that. Okay, so for this, you know, you see the first line, auto assigning not sampler. This is done automatically. Keep in mind, there are a lot of different samplers out there, okay? Of course, they are all MCMC variations, okay? NUTS is just one of the efficient MCMC samplers, okay? There are others, okay? To be honest, like different Python, different Bayesian data analysis textbook talk about different samplers, but they all based on MCMC. Okay, so so it automatically find the efficient sampler for you, and it will initialize NUTS using jitter plus adapt. These are like some options that will set automatically for you. You don't even need to set up this. Of course, you can set it up your own options, but you don't have to. I mean, the program will. You know, this library will do it automatically for you, okay? And then multi-process sampling, okay, it will find out, okay, you have 2 chains in 2 jobs, okay? So what does that mean, okay? Because, I mean, nowadays all the CPU comes with multi-processors, right? Okay, so it will automatically find like several available processes in your computer, and have each process to run 1 chain. Okay, so this basically means that the program is getting the access to 2 cores in your CPU and run these 2 chains, in parallel, okay, for you, automatically, okay? And, so nuts theta. This just means like, okay, that's the posterior that we are collecting, okay, because we call this theta, right? The posterior is theta. So I mean, you notice that, okay, it's the posterior is for the theta parameter, okay? And then, okay, so you will see this bar running from 0% to 100%. Okay, so, well, it's actually, it should be very, very fast. Okay, nowadays the computer is, I mean, CPU is quick, right? But one thing you may wonder is that it says 3,000 over 3,000. What does that mean? It means that the, inference, okay, this sampling actually collect 3,000 samples for you. But you may wonder, wait. I mean, previously we already said like we want 1,000 samples, right? And because we have two chains, so each chain we have 1,000, so it should have been 2,000, right? So how come it's 3,000? Okay, this is like, remember, like I told you, like the program, the library will automatically find the good option to set up for you, right? But in order to find those good settings, it has to, collect certain number of the samples to see if this sampling process is efficient. Okay, so actually, okay, for each chain, it is going to generate like the first 500 samples as as a mean to verify, okay, to check if like I mean what type of setting is the best for the current problem. Okay, so each chain you have, but after that, okay, let those like 500 samples, okay, initial samples at the beginning will be discarded. So yeah, for each chain, it is going to generate 500 for certain parameter tuning purpose, and discard it, and then the next 1,000, okay, for the real analysis, for the purpose of analysis. So for each chain we have that. So two of them, so which makes like the total of 3,000 samples. Okay. So the number of chains depend on number of processes in your machine. So if you find out that, wait a moment, so it is running like six chains on your machine. Well, it may just because your CPU is more powerful, Yeah, it depends on the type of your CPU. So of course, okay, if there's 6 chains, then how many samples will be collected? It's actually not 6,000, right? It's 1,500 times 6, 9,000. Okay, 9,000. Okay, so I will skip this. I already explained this already for you. Okay, and then you can use plot trace. Okay, and in the plot trace, you just feed the trace that you obtain in here. You just feed this trace to the plot trace like function from RVs. Okay, and it will automatically plot. It will automatically plot these two figures for you. Okay, the first one is a kernel is a kernel function. Okay, you can consider this as like a, you know, a smoothed histogram for the distribution of the theta. Okay, and the right hand side actually indicates the, you know, the value for each sample. Okay, and obviously because we have two chains, right? So you can see there are two lines. Okay, one blue line and one orange line. Okay, and the same thing, we have two chains on the right hand side. Okay, on this right hand side, actually, okay, the x-axis of course represent the number of samples, but the y-axis represent the value of theta, and you can see like the theta value, you know, jump around, right, from top, this is reasonable. I mean, of course, I cannot explain too much what this is until at a later time. Okay, after I explain the concept of MCMC, then you will understand more about that. But at least you can understand the left-hand side, right? That's pretty much the posterior distribution that we obtained from these two chains. Okay, and then you can also you know, obtain the numerical summary of trace. Okay, by the RVs. Okay, so so it will give you the mean standard deviation. I mean, MC error. I mean, at this moment, forget about this. I mean, this is related to MCMC. Okay, and this HPD 3%, HPD 97% means like the range from of like 94% HPD. I'm sorry, 94% HPD, the range of 94% HPD. Okay, from 0.02 to 0.64. Okay, and this efficient number, and I mean, for these two things, don't worry about them. Okay, for now, because again they are related to MCMC. Okay, so they are related to diagnosing samples. I mean, so how is this chain? Are these two chains representative? Okay, those are something we need to consider in the MCMC sampling. Okay, but for now, you can ignore that. Okay, for now. Okay, so by default, plot posterior will show a histogram of for the discrete values and the KD for continuous variables. So so you can just draw this posterior distribution by using this function, okay, which will give you, you know, based on the generated the two chains that you generated. Okay, this is like we just call AZ. Okay, obvious. AZ is based on RVs, right? AZ dot plot posterior, and you feed the trace into this function. You will draw a kernel function for you. Okay, because theta is a continuous value, so you will draw a kernel function. If it's theta, if the sample are discrete, it will generate a histogram for you. Okay, automatically. Okay, so it will also indicate the 94% HPD range as well as your mean automatically. So you can see it's actually very simple to write a program to generate the posterior, right? Okay, I really highly recommend you to try it yourself. Okay, first, of course, you need to install like a necessary package, like for PyMC3 and the RVs, and then you can try out these programs. Okay, should be very easy. Okay, so we need to, but after we get the posterior, I mean, we need to, a lot of time we need to make decisions based on our inferences, based on our analysis result. The analysis result is a posterior distribution, but we need to, some decisions that we want to make are, dichotomous. Okay, for example, dichotomous means like a yes/no question. That's the question we need to answer. Okay, but the result, I mean, that we have in this slide is continuous, right? So, so for example, like health, sick, contaminated, safe, something like those. Okay, so one of the question may be like we want to decide if the coin is fair or not. Okay, remember like we are talking about coin flipping. Of course, I mean coin flipping can be used to represent many questions that I mean, for example, like is health, sick, contaminated, safe. Okay, all dichotomous like questions can be modeled by coin flipping anyway. Okay, so come back to coin flipping. Okay, if you want to decide if the coin is fair or not, what do we do? Okay, one way to do it is we compare the value of 0.5 against the HPD interval. Okay, so the HPD interval is from 0.02 to 0. It should be actually it should be 0.02 to 0.64. Okay, and yeah, this looks more like 64. Okay, yeah. So there's something wrong with this this value. Okay, it should be from 0.02 to 0.64. So 0.5. Okay, that value is included in this HPD. Okay, so if that's the case, okay, we could say that okay. We cannot completely rule out the possibility that the coin is fair. Even though we know, okay, from this figure, obviously, its distribution is biased toward the tail, right? It's biased toward the tail. But, because the 94% HPD include 0.5. So we cannot rule out the probability, the possibility that the coin is fair. Okay, this is one way to determine, to make your decision. Okay, dichotomous decision. Okay, based on this posterior distribution. Okay, and if we want a sharper decision, we will need to collect more data to reduce the spread of the posterior. Okay, or maybe we need to find out how to define a more informative prior, because the prior that we use is flat prior. Remember, if we have a more informative prior, then the result may be more accurate. Okay, or if you are able to collect more data, because for this result, it is only obtained through 4 trials, right? 4 trials. Say if you are able to collect like maybe 10 or even 20 trials, you can imagine that this distribution will be more, what should I say, like it will be more narrower, and it will be taller, right? The figure will look like that, and obviously the 94% HPD will be also narrower, okay, which may not include 0.5. Okay, so this is one way to make a decision from the posterior distribution. Okay, so another way to make decision using the posterior distribution is what we call region of practical equivalence, okay, which is happen to be abbreviated into an interesting term called ROPE. Okay, ROPE. So this ROPE is like a concept that has been used in Bayesian data analysis very often. Okay, so what is this? Okay, we generally do not care about the exact results, but the results within a certain interval. Okay, so we call this interval region of practical equivalence. Okay, so for example, okay, take the fair coin as an example. Okay, previously I say, okay, the fair coin has to be the theta has to be 0.5, right? But in practice, do we really think, okay, the coin, the theta value for the coin has to be exact 0.5 to be fair? How about 0.5, 0.00001? It's already close enough to a fair coin, right? Or it could be like a 0.49998. Okay, so do you consider those coins fair enough? In practice, those coins may already be considered fair enough, right? Okay, so for example, okay, we could say that any value in the interval 0.45 to 0.55 within this range, if the theta is within this range, then, okay, the coin is considered fair. So in this scenario, okay, the ROPE that we are talking about is this interval. Okay, that is why, okay, because in this interval we consider the result is practically equivalent. Okay, practically equivalent. Okay, so that's why it's called the region of practical equivalence. Okay. So once the ROPE is defined, we compare this ROPE against the HPD. Okay, so obviously, because you are comparing an interval with another interval, right? So there are 3 possible cases. It's no longer just 2 cases, okay? Because it's no longer a point consideration, okay? So the first case is the ROPE does not overlap with HPD. Or it's completely outside of HPD. If that's the case, okay, remember, this ROPE, okay, 0.45 to 0.55 is the range, is the region that we consider coins fair, right? But if this region is completely outside of the normally 94% HPD, okay, then we can say that the coin is not fair with a more definite answer. We can say coin is not fair. So if another case is the ROPE contains entirely inside the HPD, then we can say the coin is fair. Okay? So for these 2 cases, I mean, they are easy to judge, right? The third case is there are partial overlaps between the ROPE and the HPD. If that's the case, okay, we cannot say the coin is fair or not. Okay, it's undetermined. It's undetermined. So compared this one with the previous, like a single point, like estimate, okay, what's the difference? Okay, first, this one is only, like, if the point is inside the HPD, we say, if the point is outside of HPD, we will say it's not fair, right? If point is inside HPD, we say it's probably fair, right? Probably fair. But first, like this exact 0.5 requirement for fair coin is really not practical, okay? Because pretty much, I mean, if you define like that, I mean, probably no coin match that fairness requirement anyway, right? Because we are talking about a fixed value in a continuous range, right? You know, like in a continuous range, I mean, talking about one particular value doesn't make much sense anyway, right? Normally, for a continuous region, we normally talk about a range instead of one single point, okay? And the second thing is like a rope approach gives us like more information. For example, we can say it's fair, it's not fair, or it's undetermined. Okay, so this is like if you know the confidence interval, okay, you will see that this actually has something to do with it's similar to confidence interval, but in the confidence interval, okay, there are some assumptions hidden behind the confidence interval computation. It's just like when you do the computation, you don't know those hidden assumptions, and those hidden assumptions really are not that reasonable. Okay, in other Bayesian data analysis textbook, it talks about like why classical or like frequentist approach, such as like a confidence interval. Okay, why those concepts are not a good idea. Okay, but here, I mean, in this textbook, we don't talk about that much. But the confidence interval, I mean, or like NHST is used, okay, to make decision, okay, in traditional statistics. But here, okay, you can see in Bayesian data analysis, we use posterior and some very simple way to make a decision from the posterior. Okay, it's much easier to make a decision, okay, based on posterior. Okay, and this simple method, such as rope, okay, it doesn't have much additional assumption. Okay, so which is nice. Okay, compared with like NHST. Okay, yeah, but if you don't know NHST, maybe forget about what I'm saying. I was talking about. But if you know NHST, maybe I can tell you some additional material to study. Okay, but anyway, so of course rope is interval, right? So how do we choose appropriate rope? Okay, this is like based on background knowledge. Okay, any value inside this interval is assumed to be of practical equivalence. Okay, so you could choose, the fair coin to be in between 0.45 to 0.55, or you can choose rope for coin fairness to be in the interval 0.1. If you do that, well, no matter how you do the analysis, the coin must be fair, right? Because that's the possible range for the theta value anyway, right? Okay, but this is trivial, unreasonable, and a dishonest choice, and probably nobody is going to agree with that, right? So basically the choice of the rope should be, reasonable and honest choice based on your background knowledge, and which can be recognized by the majority of the people. Okay? So, so we mentioned this unreasonable, region, okay? It's just to highlight the fact that the definition of the rope is context dependent, okay? So it depends on the problem. There's no auto magic rule that will fit everyone's intentions. Decisions are inherently subjective, and our mission is to take the most informed possible decisions according to our goals. So basically, you have to, based on the background, find the most suitable rope. Okay, so that's based on your subjective knowledge, background knowledge. Yeah, but at least, if you, this 0-1 rope is obviously, absurd setting. Okay, but you can set it to be, say, 0.4 to 0.6. That's also reasonable, right? Okay, or if you think like, okay, you have more demands for a fair coin, you can set it to be like maybe 0.48 to 0.52, something like that. And you see, basically it's a symmetric one, right? The setting should be symmetric, which reflects like, the symmetric nature of this question that coin is fair, right? So again, this, of course, even though we didn't say that, but you can clearly see that the rope, a more reasonable rope is a symmetric one, centered at 0.5. Okay? So you can use a plot posterior function to plot posterior against the rope. Okay? You just need to, set the rope, range, okay, when you use a plot posterior function, and it will demonstrate the rope by using this green interval. Okay? And it will also like tell you, from here, you can obviously see that, okay, this rope, okay, is completely inside 94% HPD, right? So, which tells you that under such a rope setting, okay, based on the data that we collected, okay, this coin is fair, right? Because the rope is completely inside the 94% HPD. Okay, well, it's let's take 10 minutes break. Okay, shall we? Oh, by the way, for today, I have to probably leave like maybe 5 minutes earlier because I have a meeting at another building, like at 12 o'clock, which I cannot be late. Okay, sorry about that. But well, let's take a shorter break, maybe like 5 minutes, if that's okay with you guys. Okay.